All right. The temperature, if it varies, like say deviates widely from 298 Kelvin, then maybe you shouldn't use it. And that is, let's say I'm looking at delta H of vaporization for water. And so I would say, well, will delta H of vaporization for water at 298 be the same as delta H of vaporization at minus 10 degrees C, 263 Kelvin? No, because there, at 298 you're vaporizing water from the liquid state. At minus 10 degrees C, it's all going to be solid, and you're vaporizing it from the solid state, which is going to have a different vaporization energy, going straight from the solid to the gas sublimation. And so that's what I meant. So as far as that goes. For us, though, we don't have to worry about it too much. We're just going to use it.
So there's a wider range.
No, I mean, there's certain things that just...
Like phase transition.
Right. There's certain things that, like if we're doing a reaction that involves water, say H2O liquid, H2O gas, there's a certain range. It's like batteries. For batteries, there's a certain temperature range in which that battery might function. So, for example, if the temperature goes down, what happens to the voltage of an automobile battery? Well, we could do a thermodynamic calculation to figure it out, because in the equations that we have in chapter 20, we have E of the cell is equal to E naught of the cell. Was it plus or minus? It's a little bit confusing because our delta G equation is delta G is equal to delta G naught plus RT ln of Q. But for E of the cell, it's going to be minus. And you can figure it out based on, delta G, what we want is we want a more negative delta G. More negative delta G means bigger driving force. For this, we want a more positive E. More positive E means, and so as the product, Q's products over reactants, product grows, this term grows bigger, making it less spontaneous. But what happens if we change the temperature here? How do we deal with that? And so this is all part of thermodynamics. In thermodynamics, when we change the temperature, what's that going to change? Do you expect it to change the cell potential? Because temperature isn't involved here, but we already know that this cell potential is valid at what temperature? At 298 Kelvin. And so people are very interested in batteries at different temperatures, because there's some batteries that potentially have a better voltage or better operating life or whatever. And so a lot of people were interested in high temperature batteries, because there's some reactions that you can do at high temperature that can generate nice batteries. But the problem with high temperature reactions is this: if you use a regular battery that we've been dealing with, we have to put in solutions in there, like the salt bridge and the solutions that come into contact with electrodes. And so that limits the maximum temperature that we can have for the battery. What would the maximum temperature be? Around the boiling point of water or the boiling point of the solutions. It's going to be slightly higher because we have some solutions, salts dissolved in there or whatever, but not that much higher. And likewise, we can't go too cold either, right? Go too cold. And so what I meant by using this is, within limits, like if we're dealing with an aqueous reaction, right? You got an aqueous reaction, and the aqueous reaction, I want to figure out what the temperature at, let's say, 1,000 Kelvin. You know, what the delta G for the aqueous reaction at 1,000 Kelvin is going to be. There's nothing that tells you, wait a minute, you're going to get the wrong answer, you know. You just have to know, like at 1,000 Kelvin, what are you going to have? Are you going to have much water? No. And so would it be applicable, let's say, I want to make this reaction spontaneous. It's some aqueous reaction. I want to make it spontaneous. And so therefore I calculated the temperature at which it might turn spontaneous. 1,000 Kelvin. And then it's your job to interpret the numbers. Anybody can calculate the number. In fact, there's a great quote. I should bring it in. There's a great quote about the job of the scientist. It's from, I forgot who it was from, like Pasteur, one of those famous 19th or early 20th century. Maybe it was 20th century chemist. Pasteur is 20th. Well, anyway, he said, it's, or was it? Yeah, I'll bring it in. He said something to the fact that, the scientist's job is not to just calculate the numbers. The scientist's job is to interpret the numbers. A lot of people, they think that all they have to do is do the calculation. If they get the calculation right, then that's it. But it doesn't stop there, because you have to interpret the number, and that interpretation is what I've been talking about in terms of, is it feasible? Are things feasible? You calculate a number, we could reverse that reaction. We could reverse that reaction that we tried to reverse in lab. But is that something we can actually achieve? In theory, yes. But can we achieve that? Maybe. And so, the scenarios differ. If you have an aqueous solution that becomes spontaneous at 1,000 Kelvin, you would say it's impossible, right? Even though the calculation told you at 1,000 Kelvin delta G should turn, that is, it should change sign. And so you make a comment, yes, theoretically, yes, or something. At this temperature it should, according to this equation, but, in practice it can't. I ask people to calculate the temperature sometimes, and they'll come up with, delta G changes sign at minus 175 Kelvin, and leave it at that. At minus 175 Kelvin, that's where it'll go non-spontaneous, or maybe it'll go spontaneous. And then, they leave it like that, and then I think, well, there's not enough, thinking. If they just think they're done, they've reached the finish line, they did the calculation, that's it. Well, unfortunately, it's not it. And so the same thing happens, when we make that assumption with delta H and delta S, there are some constraints to that, because, if you're dealing with an aqueous solution and you're trying to use delta H at 298 and the solution's at 1,500 Kelvin, then forget it. It's not going to work, right? We won't have cases that extreme. We won't have cases that extreme because, we wouldn't, and the book wouldn't put problems like that out there, right? And so the problems are nicely edited so that you don't have this trouble. Just like Chem 4, they wouldn't put certain problems in Chem 4 because they calculate the wrong answer. I think that's the same thing. I think that's why, that's why people know pH. To keep people safe, people know pH from 0 to 14. That's to keep people safe, right? But in the real world, you can have pHs greater than 14 and less than 0. And so it's the same thing. They just edit down. In Chem 4, you don't want to talk about pHs less than 0, and you don't want to talk about pHs greater than 14. So you make sure every single problem stays within the fenced-in area. It's just when you remove the fences, and then it's a more competitive environment in the sense that you have to fend for yourself. Nobody's there to protect you from your calculation. And you see this at conferences too. There's nobody there to protect you from. misinterpreting the numbers. Does that answer the question? So you're going to be protected. You don't have to worry about it, basically. The type of calculations we're going to do, we're going to make that assumption. Because what else can we do? Unless I threw in a problem, maybe. I wouldn't. I mean, thermo is confusing enough as it is. All right. Well, how would you figure out what the temperature, how the temperature impacts a cell? Tell me. This is what you're doing. You're going through this material repeatedly, right? And then your brain is starting to assimilate and organize the material. And then pretty soon, you could do things in your head. You can make these connections like a puzzle or a maze, right? When you learn it. And you first go through a maze, it's difficult, but after you learn it, it's very easy. Right? You learn the path. That's the analogy, the path through the jungle analogy thing. Where, going through the jungle the first time. Well, anyway, getting back to this, how would you do this? How would you determine E of the cell at a different temperature? Well, tell me what you do. In thermodynamics, you have to make these connections. They don't write out every single connection because there are a lot of ways to connect the different symbols. And so, for example, what I'd say is if you want to figure out a different temperature, we need to connect these potentials. E naught of the cell will change and E of the cell will change. Both of these, right? Or will E naught of the cell not change because it's standard? No, both of them will change. And so how do we figure out what both of them are? Well, we know that E is related to delta G. And we know how to do temperature changes with delta G. We also know that delta G is related to K, and we know how to relate the temperature changes with K, right, the equilibrium constant K. We had the ln of K2 over K1, that's one possibility, or we could do something else, with the delta G's. And then go back and figure out E. And so there's those types of connections we can make. Okay, other questions?
I had a question about ln of Q and ln of K. When do you know when to use either one?
Yeah, it's when you set, like, for example, if I set E of the cell equal to 0, then what does that tell you? That the electrons aren't being pushed one way or the other. The cell's completely dead. Cell being completely dead, that means that the conditions it is at equilibrium. There's no more change. Right? We've reached the state of dynamic equilibrium. And so Q is no longer Q. Q is Q. Q is initial, but we know something that when it's at equilibrium, Q is the same thing as K. Whatever conditions I have, there must be K. Otherwise, there would be some kind of change. Because if Q is greater than K, there should be some voltage forward. If Q is less than K, did I get that right? No, if Q is greater than K, there should be some voltage backwards. Q is less than K, it should be forward. And since there's no voltage here, Q must be equal to K. Okay, other questions?
For the practice exam, it says what is the lowest entropy possible, and then it gives you 0, and then -500 and none of this. When you say, do you mean by how we arbitrarily defined it, or like in general what
What is the lowest entropy possible? What would you say? What could you say with firm confidence? Yeah, 0. 0. I'm sorry? Yeah, this is a change. We're just talking about absolute entropy.
But there's no way to get zero Kelvin, right? So it's impossible, but it's impossible, but theoretically it's okay.
Yeah, you know.
But it's asking for the possibility of the lowest entropy. I don't think the zero can be possible.
Well, we don't know what the future beholds. I mean, I'm just saying, okay, the lowest entropy possible, whenever you have a question like that, then you would select the best answer. And so, was there a none of these?
Yeah.
Yes, none of these. And then if
So
you...
it's none of these?
No, it would be 0. Because that's the third law of thermodynamics, the third law of
That's
thermodynamics.
arbitrary, like you just said.
It's not arbitrary.
There's no.
No. You have to think of it this way. You have to think, if there is a perfect crystal at 0 Kelvin, how many different positions can each atom occupy? Yeah, there's only one. And so therefore the entropy must be 0. And so any perfect crystal, and this is something you can extrapolate down, because at 0 Kelvin, is there any atomic motion?
But we cannot reach zero Kelvin, right?
Well, okay, I see what you're saying. You could write that in. You could say none of these because 0 Kelvin is impossible to reach, right? But the third law of thermodynamics, we have to rely on this here, because even though we can't, you can get very close to 0 Kelvin, and you can measure heat capacities very close to 0 Kelvin. You know, but the last of this is just extrapolated to 0. That is, the last experimental data is very close. 4 Kelvin is very easy to reach, and then you can go colder than 4 Kelvin. And so based on this, right, this is how we're going to get, we're going to get the area under this heat capacity curve, and that's going to be related to the absolute entropy. Now, the laws of thermodynamics, when you talk about the laws of thermodynamics, a lot of people think, well, what is a law? And so we start off with what? And in fact, the laws of thermodynamics were developed before atoms, ever came to be. And so when we're thinking about the laws of thermodynamics, how are the laws of thermodynamics developed? They're developed from, well, how are laws typically developed? Observations, right? Patterns in nature, observations, and then they came up with the law. And so a lot of people say, well, what's the theory? What's the theoretical foundation for the laws of thermodynamics? Why should I believe in the laws of thermodynamics? And this third law came later, and so a lot of people have been trying to disprove the laws of thermodynamics for 2 centuries now? The laws of thermodynamics were developed in the 1800s, and people have been trying to disprove them because, what is the fundamental theory underlying? Well, a lot of these things can be derived from statistical thermodynamics, when you look at the atoms and molecules and that kind of stuff and the ways they behave. But, you don't need to believe in any of that stuff. And so, why should you believe in the laws of thermodynamics? Do you have a good answer for that? Why do you believe in the third law? Why even believe in the second law? Who said that the entropy of the universe has to increase? Who observed that? You know, why should you believe that? Or even the first law of thermodynamics, I don't really know. Is energy really conserved? Is it really neither created nor destroyed? Well, you know, that's, what about this when we get to nuclear chem? What's going on there? And so, laws of thermodynamics is something that is just taken without proof. Where's the fail-safe proof for that, right? And we don't have it. And so the same thing with this, you know, this 0 Kelvin, do you have to actually observe it for it to be real? No. The question is this: what is the lowest possible entropy? Well, it would be 0 Kelvin if we could. I mean, not 0 Kelvin, 0. If we 0 joules per Kelvin, if we could go there that far. But could it go lower than 0? No. And so this is what we call the limit of that. And so the limit of that, and that limit, okay, is different than what I'm talking about in terms of, you know, if you have an aqueous solution at 4,000 Kelvin. An aqueous solution at 4,000 Kelvin, is that something that's possible? No. Or the limits of our equipment. You know, the limits of our equipment would be like, okay, I need to heat this up to 4,000 Kelvin. Can I do it? Well, if I had something to do it, but then I started talking about phase changes. At 4,000 Kelvin, you know what happens to gases? Gases turn into plasmas. And plasmas are going to behave a lot differently than your typical gas. And so there's a phase change there. And so when I'm talking about those, that's a little different. Okay, we can't reach that temperature because something's going to happen. Something's going to change, you know, which is different than this. This is going to be the absolute zero of entropy. The absolute zero of entropy is 0. Is what I meant for that. It's not whether we can reach it practically or not. That's a different, you know, than a little different because, you know, we're saying we can't reach 4,000 Kelvin because that's not an impossible temperature to reach. It's possible to reach that. It's just that it's going to be impossible for this particular experiment. Also, when you get to, let's say, when you get to 1,000,000 Kelvin, you get to 1,000,000 Kelvin, molecules can't exist, right? Everything's all broken apart. And so that's it. What I want to know, sorry. What is this? Minus 287 for fluoride. Is that an oxidation potential or reduction potential? Minus 287. This is an oxidation potential. Now, this is minus 287. Is that the lowest oxidation potential possible? No. Tell me the lowest oxidation potential possible. I want to know the absolute lowest oxidation potential possible. You know, every time somebody finds something lower, then somebody will come up, oh, I can find something even lower than that, right? Like, easy. For me, it's easy. Like fluoride, a fluorine would be lower, right? And then somebody will go, no, that's not lower. Fluorine plus is lower. And I go, oh no, I got you fluorine 2 plus. You know, because those are successive oxidations, and that's going to cost you a lot more energy, so those are going to be much, much lower, right? But you tell me where the limit is. What is the lowest? Who knows, you know? So somebody's going to come up with something, or find something even harder to oxidize, right? Whereas, you know, so if you're looking at the minus 500 or whatever it was, what was the other one? Minus 500, you know, who knows? if that's the lowest in terms of the relative scale. We don't know, but we do know 0 should be on the absolute scale. In fact, the 500 should, the minus 500 should be even higher than 0 on the absolute scale. So I know I was talking about, oh, this is not a feasible temperature. You know, this is not. Well, this is different because this is. This is something that we don't. This is the same thing with the Kelvin temperature. We don't abandon the Kelvin temperature just because we can't get to 0 Kelvin. I mean, 0 Kelvin is the coldest. We can't go negative, is what it means. Whereas I want to know, you know, what is it, negative 500 volts, negative 5,000 volts? What's the lowest oxidation potential? All right, other questions?
Yes. Number 7 says entropies can be determined from theory or experiment. I know they can be determined from experiment, but not for theory. From theory?
Yes, from theory. How? Well, you know, a perfect crystal has only one way to arrange things. Then Boltzmann came up with this theoretical equation for positional entropy. S is equal to K ln of W. And 1 is the lowest possible ways, right? Can you have 0 ways to arrange things? No, so 1 is the lowest number you can get. So 0 would be the lowest entropy. Okay, other questions?
This one, which one, number 11, it says, which of the below results is an increase in entropy? So we selected delta U greater than 0 and delta S greater than 0 and delta S, well, it's the same thing. You have the same options, right? But what about, so far we have delta U greater than 0 and delta S greater than 0.
What was the question again? Which one results in an
increase in entropy?
In an increase in entropy. Well, for sure, delta S greater than 0 is going to result in an increase in entropy.
And then delta U greater than 0 as well.
Delta U greater than 0. Well, delta U greater than 0
Increase in the internal.
is an increase in internal energy.
And that causes an increase in entropy.
Why would it cause an increase in entropy? Why would an increase in internal energy cause an increase in entropy?
More disordered.
Why would it be necessarily more disordered? No. Remember back in Chem 1A, whenever we're looking at a delta U or delta H, the initial temperature and the final temperature are the same thing. And so, yeah, if delta U is greater than 0, that just means that U initial is down here, U final is up here. So we have a delta U here. Right? And so why are you saying that? And then we know U final is equal to what? U initial is equal to what? Q. EK plus PE. Yeah. EKF. EK initial plus PE initial. And then for thermo, we always do this because we don't want to do two different things. Whenever we change chemical potential energy, we don't want kinetic energy to change. It can change, of course it can change, but then you'd have to factor in two deltas here, the change in the kinetic energy and the change in potential energy. Change in kinetic energy is usually given by Q is equal to, you know, MC, or the amount times C times delta T, right? And change in potential energy is usually given by Q is equal to amount times delta H or delta U. And so we don't want to mix those up. Otherwise, when we have the equations, we have to have two, you know, the kinetic energy part plus the potential energy part of the change, right? And so this is what we talked about in Chem 1A. We talked that the temperature has got to be the same. There's no change in the temperature. This is a state function.
But if
Mm-hmm.
there is no change in temperature, delta U should be zero, right?
Hmm?
The delta U should be zero.
The delta what?
Delta U should be zero.
No. Delta EK is 0. Delta U is equal to delta EK plus delta PE. When we do thermal, we don't want two terms. We just want one term, so we keep the temperature the same. Right?
More possibilities for like bond
Hmm?
strength and stuff?
What's that? More possibilities for?
For like the bond strengths and stuff in different ways to be
Yeah, but you mean a higher potential energy? More possibilities? It depends. You know, it's not just because there's more bonds. There's usually the same number of bonds. It's just the bonds are weaker at higher potential energies, and bonds are stronger at lower potential energy. And so how do weaker and stronger bonds impact? Mhm.
If they're weaker, they can move further apart and stuff. And I think there's no way to.
Well, let's look at this. Let's look at, you know, the thing is, this is kind of abstract, so just put an example here. What's an example we should use? We should use something like photosynthesis. How about that? Plants do what? They take CO2 and water. And what do they make? Well, let's make some glucose. C6H12, O6, and oxygen. Keith, how are you telling me that the entropy is increasing because the bonds are stronger or weaker? Is that what you got?
Well,
You don't. So this is.
I thought it meant like if you just pick the same molecule and increase
Yeah,
its
same
chemical energy, not
molecule,
change to a
like
different
evaporation.
molecule.
That's possible too. But, you know, this is just the general delta U. So we could have H2O liquid, right? Goes to H2O gas. This is an example where the potential energy, did it change? Delta U is the same. Delta U is equal to delta EK plus delta PE. Water is water, so the potential energy doesn't change. It's all kinetic.
So yeah.
But delta U is equal to EK plus PE. I mean, delta EK plus delta PE. And so how can you limit it to this? Yeah, in this case, yes, the entropy did increase because we're going from the liquid state to the gaseous state. In this case, did the entropy increase? Maybe. Or did it stay about the same? Hard to tell. I mean, O2, CO2, but I would say the entropy likely, because we got 6 moles of gas, and then we got this solid versus liquid, and so liquid typically has higher. I would say the entropy actually decreased. And so this is like the laws of thermodynamics. Somebody's always trying to disprove the laws of thermodynamics. Well, I just disproved this, right? The entropy doesn't increase because delta U. I mean, you can't take those hand in hand. That, oh, delta U goes up, the entropy must, but we're talking about positional entropy, right? There are two types of entropy. There's positional entropy and energy entropy.
So far.
And so,
delta is greater than 0. The delta U wouldn't really influence the entropy.
well, in this case, we were talking about delta H. Delta H is the heat of the reaction. And we're talking about heat being dumped in an exothermic reaction. And so if you have something like this, like delta H is less than 0, then what can you say? When you have delta H less than 0, then we know that delta H is defined as what?
Q inverse.
Well, delta H is defined as QP, right? QP. And so here, what we're having is we're converting. This is what we were talking about, converting. Let's say converting. In this case, we're converting in terms of chemical potential energy. Like, for example, if we went down this way, we're converting chemical potential energy into heat. Now, that's for chemical potential energy. This would be a physical process when we're going from H2O gas down to H2O liquid. Is this a change in chemical potential energy? No, this is just a change. You got a hot object. This is at T hot. This is at T cold. And so all we're having here is just a kinetic energy transfer. We're taking heat from one object and giving it to another object, right? And so this is what we call heat transfer. Heat transfer would be different than something like this, where we're converting chemical potential energy, like methane, plus 2 O2 yields CO2 plus 2 H2O, liquid. This is converting chemical potential energy into heat. And so here, when we're thinking about what's happening with the entropy, versus here, maybe it was too loose with my definition for that. But would you say that this qualifies as entropy going up here? No, so let's not consider that. As entropy of the system going up.
But in some cases it can.
In some cases it can, like this. This is heat transfer also. And so the entropy of the system is going up. Whereas the entropy, I don't know, did I say anything about universe or system or surroundings on that? No, I just said delta H and delta.
We have two more options. We have delta H less than 0 and delta T less than 0.
Okay. Delta T less than 0. Well, let's look at delta T less than 0. What would you say about delta T less than 0?
Decreases entropy.
That should decrease the entropy, right? You go to lower temperature should lower the entropy. And then what about delta H? It, in this case, if delta H is less than 0 here, if delta H is less than 0 here, then the system entropy would decrease. But, you know, the delta H, the energy entropy, when we're looking at it, the energy entropy with the delta H less than 0, is delta H favorable? That's a driving force, right? And so the entropy of the universe must be increasing. But you could argue it either way. I mean, if you want to leave it at that, because I should have been more specific about what I was talking about. Sorry. So, that particular question I'll probably be more specific on for your test. Okay, what else do you guys know?
There is number 19.
Mhm.
It says iron 3 oxide and carbon monoxide give you iron and carbon dioxide. Does it either increase or decrease, or more information required? It shows more information required. It's the same, but what do you say?
More info.
Which one was it? I mean, what was the reaction again? Iron?
Iron 3 oxide,
Okay.
So,
solid, plus 3 carbon monoxide gas gives you 2 iron solid plus 3 carbon dioxide gas.
Okay. And you want the delta?
Increase, decrease, or more information required for delta S?
Yeah, more information required. Delta S.
It's because of the moles of gas are the same.
Yeah, moles of gas are the same. This one has slightly higher entropy than this, right? But when you look at the solid, you know, this one should have a lower entropy than this. We don't know.
So,
Okay, other?
Delta S reaction is greater than 0, then the delta S inverse is greater than 0 in that way.
Delta S of reaction is greater than 0?
then the delta S of the universe will be greater than 0. That's true. Isn't it like the entropy of the reaction increases, doesn't that increase the universe?
Oh, it's false, yeah. It's not true.
Delta S takes surrounding us.
Oh, yeah, because delta S of the universe is, equals what? Delta S of the universe equals, that's the reaction, plus, yeah, the surrounding. We don't know what's happening with the surrounding. So it can't be true. It might be true, you know, but we need more information. Okay, other questions?
Yes.
Uh-huh.
For number 5, it says which is used primarily to predict the reaction driving forces. And I put second law only, but I wasn't sure if that's primarily used or not.
What were the other choices?
First one.
And none of these.
Yeah. Second law. That's correct. Okay.
total gases, when ideal gases are mixed, circle all, so delta U is less than 0. Delta H less than 0, delta S greater than 0, delta S less than 0. Because ideal,
Yeah, when ideal gases are mixed,
there's no IMF.
delta S is greater than 0. That's it. The energy of an ideal gas is only kinetic, and therefore if there's no temperature change, then that's it. Nothing's going to happen. There could always be temperature change, because when gases expand, when gases expand the volume, what happens to the temperature? Usually when you expand a gas, the temperature goes down, right? But if you go back in chapter, what is it, 6 or 7? There's a homework problem there called adiabatic expansion versus isothermal expansion of gases. Do you guys remember adiabatic versus isothermal? Adiabatic is you do it in a totally insulated container. And so if a gases expand adiabatically, the temperature changes. Whereas isothermal, you do it where it can exchange heat with the surroundings. And so when you expand the gas, the temperature can remain constant. But thermodynamics, does it seem overwhelming? Yeah, well, not yet. A lot of people will say yes, it's totally overwhelming, because all these things to keep track of, potential energy, kinetic energy, everything else. And then a lot of people have to take thermodynamics, including biologists have to take thermodynamics. And so it has a bad reputation, thermodynamics. And so the best thing to do is just go back over and over again, because, like I said with the units, a lot of people have trouble keeping track of units in stoichiometry calculations. Well, that's a bad habit, because when they get to thermodynamics, they're going to have a heck of a time, because nobody keeps track of units, but except in their head in thermodynamics.
Are we going to have all the equations on the board again?
Yeah, the major equations would be on.
Would we be able to make like a little card to write them on?
No. If I allow no cards, I have to make the exam harder.
No, that's hard.
I have another question. It says circle all below can potentially change delta G naught, and it gives you temperature, concentration, and pressure. Temperature would definitely. That's for 19. It's 19B28. It's the other test.
Okay, temperature,
It's number 10.
concentration, and pressure.
Concentration and pressure for delta G naught.
For delta G naught? That's a trick question. Think about it.
Temperature would definitely change it.
Yeah.
Concentration. Pressure you can't. And you can't change concentration, so just the temperature.
It's only temperature.
Because delta G naught is number 11.
Actually, you know what? I need to see the questions. Sorry. Well, on the one hand, I don't want to talk anymore about this, but on the other hand, just because I don't want to get too far behind.
The online Q&A platform.
It's concentration and
I'm sorry? Let me know that. Thank you.
Because I guess
All right, what number was that?
it is number 11.
11. Circle all below that can potentially change delta G naught. Temperature for sure. Concentration, no. Why?
Because it's under the standard conditions.
That's under standard conditions. Even if you change the concentration, it's not going to change delta G naught because delta G naught is just for 1 molar.
And the pressure is essentially.
Right. This is, you know, in Chem 1A, I use the speeding analogy. You know, I'm driving, let's say, 75 miles an hour in a 65 mile an hour zone. You know, what's the speed limit? Well, it doesn't matter how fast you drive. The speed limit is 65, and so delta G naught, it doesn't matter how concentrated or how dilute it becomes, it's still fixed. Same thing with pressure. So just A.
What about the one above? Is it all of them?
Circle all below that can potentially change delta G. I decided to put 10 and 11 paired because I got a lot of wrong answers when I just like put something like 11 or something like 10 alone. That can potentially change delta G.
All of them.
Yeah. All of them. Although, you know, the coupled reaction is debatable. You know, if you didn't select that, it's okay if you just say, you know, the reaction is going to be different. You know. And so, but all of them could potentially change, and all of them are used. These were the 4 techniques we talked about in changing delta G. All right, what else?
What about 12 and 13?
Delta G naught at minus 500 kilojoules is large. That's just memorization, you know. Should have talked about it before. In fact, that is not just large, it's huge, right? Big. Driving force.
What do you mean by it? Why would it be large?
You memorize it.
It would be on a scale, 0 to 50.
So what would like one that's like negative 250, would that still be considered large? Would that be?
Negative 250, what do you guys say? Large. It's large. Did you guys get it? What were the cutoffs there that we talked about? 50 to negative 50. So I missed that there. It's minus 50 to 50. Beyond that range, we consider large. And you can figure it out yourself too, but just by looking at the table with K and delta G in the book. All right, what else? Like 13, I wouldn't, you know, 13, I wouldn't give you that equation. I just give you the basic equations. You have to figure out all the relationship equations. But 13, you could figure it out. I mean, you can just look it up in the book for the answer, you know. What is the answer? This is very easy. Delta G naught is equal to minus RT ln of K. I'm going to give that equation probably. Might not make you derive that one.
That's D0, right?
And so you just solve that for temperature. And so what did you say, A or B?
G naught cannot.
It's, I'd say B.
Because G naught is 298.
This is circular. How can you know the temperature before knowing you're calculating the temperature, but you're supposed to know the temperature before you calculate the temperature? It's impossible.
Well, at 298, it's the correct one. We just know the temperature, but it's.
Then why do we need to solve for the temperature? You just say it. Oh, the temperature is 298 Kelvin. There's no need to solve it.
Right.
Are you saying the equation not solving?
You just said they were, you just like derived.
Well, it didn't say the equation T equals 298 is equal to minus delta G naught over R ln of K, did it?
Yeah.
It didn't say that. If I said T is equal to 298, which is equal to minus delta G naught over R ln of K, would you say that's true? Well, yeah.
How is it impossible to get that if you just say delta G is 0 and you say that?
Why is delta G 0? How? I asked you this question before. I don't know if you were here, Keith, but I asked the question, how many delta G naughts equal to 0 do you know? And I said I could think of one that I've seen. How many have you seen? Delta G naughts at 298 Kelvin. Do you remember which one I said? Where I said I know one of them at least? Do you remember me mentioning this?
Water?
There's only one delta G naught. I didn't mention it exactly like that because I said something. When delta G naught is equal to 0, what is K equal to? 1. How many Ks equal to 1? Do you see? This is what I asked you. But it's the same thing as asking you how many delta G naughts at 298 Kelvin. It's the exact same question. At 298 Kelvin, do you know? And so how many Ks equal to 1 have you seen at 298? In fact, I thought I wrote it on the board, rare, that delta G naught is equal to 0. So why are you telling me delta G naught is equal to 0?
No, I said delta G, not delta G naught. Just delta G, not delta G naught.
Delta G naught, I'm not exactly sure. And anyway, we don't even know what delta G naught is. It doesn't have to be 0. Well, why is it very confusing, this one? Why is this question very confusing?
Because can't you derive that?
Derivation is correct.
You can derive that from delta G equals delta G naught plus TR ln of Q. So if you say delta G is equal to 0, then Q is equal to K, then you can rearrange it to get that.
Yeah, but this is what I mean by there's nobody that's going to stop you from making a mistake, right? As you go on, you got to be more especially careful. This is something I learned as I was progressing, through successively higher science classes. Is that, boy, things used to be so easy because, we wouldn't see an equation like this. You just leave it off and then just know these equations. That's all. Right? But this equation will get you into trouble. This is, like I said, sure, go ahead and do the calculation for me. Lots of people do. I'll tell you, maybe 30% of people on the exam will do this, will solve this equation. And so, okay, they want to know the temperature. Let's say I want a K of, give me a K value that you want. What was the K value that we looked for earlier? What was it? 0.1 squared, or 0.9. What was that K? This is the one we did in class. Did we do this one? 0.01. I don't remember if this was it. Where did this come up? Where did this K value come from? Without looking at your notes, where did the K value come from? I can't remember if this was the exact same number, but where would we get a K value like this? What was the question, the context of the question? Look in your notes now, then if you don't know, you should know. I mean, the day before the exam, you should know where you might see a K like this. When I look at this K, I see, you know, maybe it wasn't like this. I don't remember. I got to go back and look. And in fact, I can go back and look because I'll just bring it up since we're... Well, I wasn't planning to spend this much time going back through stuff, so in order to catch up, I'm going to switch to PowerPoint mode. Lets me go a little faster. For chapter 24 and chapter 25. You can download the PowerPoints though beforehand to take a look at the covering. But where did we see this? Well, we saw this in this problem here. Oh, it wasn't, sorry, it wasn't, this is, I think this was the problem, except I made a mistake here, maybe. Remember this problem, number 77?
Yeah.
We wanted 1% reaction, equal molar. And so it wasn't 0.1. This would be more like what percent reaction? This would be like 10% reaction. You remember? It's going to be more like, I think what we did was, it was 0.01 squared and 0.99. Was that it? 0.02, that's right. 0.02 squared over 0.99. Okay. And what was the K? 4.08 times 10 to the negative 4. All right. Remember, I'm doing this one because we already did the calculation. We did the calculation using the correct formula. 25% of the people who get a problem like this will use this formula. And you tell me, is it right or wrong? 25%. I'm asking at what temperature are we going to get that K value, right? Well, they go, oh, T is equal to delta G naught minus delta G naught over, well, delta G naught is the RT, ln K, so the R ln of K. And so what was the delta G naught that we calculated from that problem? Does somebody have it in their notes? The delta G naught from that problem. It was pretty positive, as I recall. But you know what? This one's so easy. This one is so easy because you know what this is? This is 2 times the delta G of formation of NO. And so if you don't have it in your notes, I can find it really quick because this one requires no calculation at all. We just go over here to Appendix D. So delta G of formation is 86.55, so double that. It would be 180, 160, 172, 173, 1. 173, 1. So that's a minus, a plus 173, 1. This is in kilojoules. This is for 2 moles, so I'm not going to bother writing the moles. 8.3145 joules Kelvin, ln of K, 4.08 times 10 to the minus 4 gives us a temperature of what? Maybe not up to 25, maybe only about 15% or 20% of the students. It depends on the semester. Semester by semester it varies how many people use this equation. Uh-huh.
Wouldn't that equation be correct if you just realized that you need to use a different delta G naught? Correct?
Yes.
So it's not impossible that that's a correct derivation.
Right, but how are you going to get the delta G naught? How we get the delta G naught is the delta G naught at temperature T is equal to delta H at temperature T naught minus T delta S at temperature T. And then we make the assumption, oh, this is going to be close to 298 Kelvin. This is going to be close to 298 Kelvin. What should I assume for the temperature? Should I assume the temperature is also going to be close to 298 Kelvin?
No.
Then how am I going to solve it? Tell me how I'm solving it.
Well, you can just plug that in.
How can I just plug that in?
We need temperature because
How?
when you do a delta derivation,
This is impossible. Do you see this is impossible? You'll see this is impossible if you know all the equations. If you know all the equations, then you go, oh, that doesn't work. This doesn't work, right? And so what you got to do is you don't memorize this is impossible. You memorize all the equations, you know, and then you make the connection. Oh, this isn't not going to work. This is just not going to work, right? Because you know the thing is, I can tell you, but you know when somebody tells you memorize this, then you forget it, right? The only way you memorize things is that you figure it out yourself. You know, this is why when we're looking at the numbers, you know, delta G, I wanted to go to the table and look at the table and come up with the conclusion with you guys. You know, above 50, below minus 50, you know, because it's gray, it's debatable. You know, some people might argue with you. But if they argue with you and you memorized it because this person told me that, that's not going to suffice. So what you do is you see, okay, that makes sense. You know, I can make my own argument for this, right? And so the same thing with an equation like this. I was trying not to say memorize that this is wrong. I was trying to say that, you know, this is how we figure out that, you know, this is impossible. Kind of thing, sorry. Well, you figure it out yourself, you know? Either memorize it or figure it out yourself. That's all I can say. I mean, we went through why. And I spent, I don't know how long, how much time did I spend on this talking about why you can't solve this equation? I don't know. Maybe not enough time. Probably not enough time. Not enough time, but you go through every single variation. How many ways can you, this is why I always ask, how many ways can you determine delta H? You should know all of them, right? How many ways can you determine delta G? You should know all of them. And then you'll figure out, oh, not possible, unless there's a hidden way that you haven't seen, you know? But there isn't. And so, yeah, we're solving for T, but we already have to know what T is. This is why, you know, it helps sometimes to write little subscripts. But then can we just go ahead and assume that the 298 version will work? Well, assuming the 298 version will work is just like assuming the temperature must be 298. Is that a safe assumption? No, that's an awful assumption. All right, does that clear it up? Yes, that is absolutely the correct mathematical derivation. There's nothing wrong with that derivation. It's fine. It's just impossible to solve. Well, maybe somebody, you know, well, that doesn't stop. This is why I say, the fence is removed, at least some of the fence is removed. I say, you're welcome. Go ahead and do the calculation. I want to see you do it. Please do it. Because then grading will be easier. This is wrong. Wrong. No. Actually, I don't want to see anybody do it. I just, the easiest thing is when everybody does it right. Then that makes life much easier. But then you get all kinds of weird variations because some people will throw on all kinds of weird equations up. I don't know where they came from, but so this is better than, I don't take off a huge amount of points. But I do every semester. Somebody does this. And that's why every semester, almost, I put something like this. Not every semester. Something like that. So what do you say? Okay, derivations look correct. Go ahead and do the calculation. Oh wait, you're right, Keith. I shouldn't use the delta G naught at 298, which was 170.1, was it? Something like that. So tell me what delta G I should use.
It's just delta H minus delta F. Find the delta H minus find the delta F.
It's the same number.
Well, you just have to keep to your variable.
Just delta G. Instead of delta G.
Just don't assume that T is 298. Leave it as a variable.
But then you never know.
Yeah, that's exactly what we did. We did that. Remember, we did this already. We said it's minus delta H minus T delta S. And then we came up with, after doing some rearrangement, R, ln of K, we came up with an equation that we could solve, which was that T is equal to delta H delta S minus R ln of K. This one is okay.
That's what I don't understand, because doesn't that lead you to that as long as you understand that you have to plug in delta H minus T delta S?
I see what you're saying. You're saying that as long as you understand this,
Yeah.
right? But this is delta G. Delta G, is it possible to put the delta G value in there? No. That's not possible. In terms of delta H and delta S in this form, it is possible. But we can never get the delta G value. And so that's why it's impossible. The reason, this shouldn't be a surprise. This is something we talked about. I talked about this equation. All this is you can argue all you want, but the situation is this. What's more important in studying for tests? Studying the book or studying what the instructor says? Even if you don't agree with the instructor, even if you hate the instructor and despise everything the instructor says, are you going to? No. What you want to do is, if you want to at least get a decent grade, then even if the instructor says this and you don't agree with that, then you probably are going to, And so this one is something we talked about, and so this shouldn't be a surprise at all. I mean, some red flag should have come up with this equation. That is the delta G. We can't use that. This is a dangerous equation. This is a dangerous equation with potential for mistake, right? And so if you were to use this equation as written, the delta G value we get from the book. I got a whole table of delta G values here. I got a whole table. Oops, where is it? I have a whole table of delta G values here. NO You know, if it's 1 mole of NO, this is my delta G. Just plug the delta G in there. Go to it. Is that what you're going to tell somebody? It doesn't work. I got a delta G here. I plug it in there. It doesn't work. It would work if I had foreknowledge of what the temperature is. You know, then it would work. But how can you argue? Well, it would work if you knew what the temperature was before that, but you don't, so it doesn't work. If you rearrange it, then it works, you know, but we aren't solving it in terms of delta G. Is there any delta G in here? Oh, this is different, yeah. That's the thing with thermodynamics. With thermodynamics, you have delta H, delta U. You know, one is delta H valid, one is delta U valid, right? Even though you have an equation for delta U, and this is the whole point I was trying to make in Chem 1A. Even though you have an equation for delta U, and it's correct, when I burn methane here, am I going to get the same amount of heat from my delta U calculation? Well, my delta U calculation is correct. The number is correct. Will I get the same amount of heat when I burn it here? No. We talked about that. We'd actually end up with less heat. And so, well, anyway, that's probably not the best way. But I don't want to spend more time on this particular problem. Just memorize that there's trouble with that equation. This should at least throw up a red flag, you know, because there's nobody telling you it's wrong. You have to come up with that yourself. All right, what else was there? We don't have much time.
Well, 14. Should be true.
Is 14 true?
It's
False.
It's not.
False. You would know that. Go back and to look at the table between delta G and K, and then remember we were talking about the plus 50 and the minus 50? Go back and look at that table where I got the number plus 50 and minus 50. It's delta G related to K. It's in the chapter. And then you'll see that 14's got to be false. Well, since we're at it, what else? What else? 15?
Yeah.
What is delta G naught at the formation? Oh, no, delta G naught for the reaction? Plus 474.2. 16, calculate K at 298 Kelvin for the reaction. Cannot be B, or can it? Yeah, it can be B. This should be highly unfavorable, so if you're going to take a guess, it's got to be B or C. Probably pick B as a guess. Or you could do the calculation. This one, would the equation work? K is equal to E to the minus delta G naught over RT.
Yeah.
Will that equation work?
Yeah.
Yeah, that's fine. Equation works.
But if it changes temperature, it won't work. If it changes temperature, it will.
No, it won't work. Okay. Did you guys go through these already? I don't want to be a spoiler on this because these practice exams are, you're supposed to go in and see, you know, get a good assessment of it. 17 similar to what we tried to do in the lab. Did I calculate this yesterday? Okay, we already did 17 then. Okay. 18. 18 looks familiar, doesn't it? Should look awfully familiar. This is why I always say, you know, if you're going to study something, you should study the The notes. Because to be honest, when I was a student, what I found the professors put on the exams was the stuff they talked about. The problem was with remembering what they talked about, because I usually forgot like 80% of what they said. And so the exam. All right, unfortunately, I guess we're out of time. So tomorrow, I mean, not tomorrow. Yeah, tomorrow, what I normally do is just do some questions at the beginning, but tomorrow I just need to lecture, just finish up chapter 20 with the electrolytic cell. So I'm going to lecture a little bit, not much. We're pretty much done with chapter 20.
My notes, I have this equation over here. Down the road.
Well, you need to multiply by -1.
Oh,
Okay.
How can you guess that it's,
Oh, because does water decompose into hydrogen and oxygen? Like beaker water, spontaneously? No. And so it's unfavorable. And so that means the K should be very small. It should favor reactants with water. And so B and C, otherwise this is hugely favorable, hugely favorable. And so between these two, and then you could just do the calculation. But if you were running out of time and had to guess, you'd probably say hugely unfavorable.
Should we stop?
Oh yeah. Thanks.